Hello guys, good afternoon. So today we'll be discussing some important procedures of the slabs, particularly to the slabs. So there are a lot of ways on how to approach the slab analysis, and we'll be talking about each and every methodologies as we go along the discussion of this. So let's discuss first some basic considerations on how to scrutinize types of slab systems that we are going to study and analyze. So there are basically five different slab systems. The first one is the flood plate system, which these systems actually um, not okay. This is not commonly used in building framing, building framing systems simply because it has to be supported by some of the structural systems such as seals or base frame to ensure that it will be adequate enough to resist the earthquake or seismic forces, including the wind forces, in case the framing is subjected to such natural forces. But the flat plate are very common to areas where there's no high risk in terms of seismicity. So for high risk seismic regions, this flat plate is not really critical. So while the flat slab system are just basically the same as the flat plate system, the only difference is that in the flat slab system, we are now considering some inclusion of drop panels, okay, and color particles to increase the resistance to puncture shear. So if you happen to see flat slabs, okay, or simply flat plates wherein the columns are directly connected to this slab, so the tendency for this system is to be subjected to very strong punching shear here, okay, which causes the slab to separate near the edges of the columns. So what this flat slab do is that we add up some uh, drop particles here, what you call color particles and drop panels. And so maybe you can see some layouts on the near columns, the slab area regions near columns to be having a thickened plate system here, which are called drop panels, and these are called panels. So just to increase the strength due to the punching action of the column uh, due to gravity loads. It may be a part of seismic forces that is developed when they actually process the earthquake or whenever process moves, no? The building frame matter. So for the one-way slab system, um, this is just the basic system that we have studied. Basically, the approach on this is a simple view analysis. Okay? So the analysis of one-way slab system is just similar to beam design. And for two-way slab systems with beams, this is the most common. The most common that we have been using so far with the frames, and the waffle slab system, which is not so common, actually are very efficient, and the panels are very long, and which means that the slab has a tendency to be subjected to excessive reflections here. Okay, so these are simply built slab and waffle slabs, which you can see normally see on very old structures, having span banks rather than the usual 6 by 6 panels. Okay. So for the stages of slab behavior, just like beams, we have uh, 4 stages. We have the crack elastic, the crack inelastic, and the plastic stage. Okay. So in the beam behavior, normally this plastic stage is normally not included in basic discussions, but eventually for nonlinear analysis, the beam behaviors also has also this stage wherein the formation of plastic hinges are expected not to allow not the member to behave in the beyond the elastic range, which is supposed to nonlinear inelastic ranges. Okay, so for the crack elastic stage, this is simply a plain concrete case. Okay, so just like beams, we have here the simple flexural analysis or elastic analysis. But this is only good for very short term loads. So for the crack elastic stage, we have here the WST method being used when we limit our FC around 50% of FC. And remember the formula for the allowable stress FC is equal to 0.45 units 0.45. A slight factor of speed is given to add on this 0.50 FC in terms of the allowable stress. So elastic analysis is of course done using a lot of procedures, no? The elastic and assumptions rather uh, regarding the material, elasticity, homogeneity, and isotonicity, which are very uh, inaccurate if we are going to look at RC materials. Elasticity may be regarded as still okay, good. No? So reinforced concrete is still an elastic material. But in terms of homogeneity, reinforced concrete is actually a highly heterogeneous material. So because of the components, okay? This material is made out of stone, gravel, sand, hydraulic paste, some additives, so it makes the homogeneity a little bit under pressure. And when say isotropic, homogeneity are actually properties that goes hand in hand. So if it is non-homogeneous, so then you can also say that it's not isotropic. But these assumptions are just done to simplify our computation later. Okay, so the flexural stiffness is no longer constant, and this makes it non-prismatic and no longer isotropic because of the also the effect of rocks make sure isotropic property also a big question. So the justification is that in the test it indicates that the elastic theory predicts the moment adequate to be forced to yield. So in the elastic stage, we are normally concerned with the working stress approach. Okay? So for the crack inelastic stage, which has something to do with strength design approach, the reinforcement is now yielded, so this is now an SD approach. The slab is very under reinforced, so make it ductile. Okay? So very ductile, so it makes it more to behave more of a ductile element. So therefore, it has high rotational capacity. So large deformation or rotation is expected. Is expected. But since it can redistribute moments, then the ductility is good, no? So it will not collapse very sudden. It will not be approaching the node of failure. Okay, so it develops plastic hinges and redistribution. So we have discussed this in our redistribution of moments in beam. So is similar, not the same, but very similar to slide analysis. So here's now the plastic design or the nonlinear analysis. Okay. So after the formation of the plastic hinge, you have a failure mechanism in the slab forms. The very flat compression arc assumes the supports are rigid, of course. So this stage normally is not accounted for in the design, but in the performance. We're considering the performance of your building, then you can say that this plastic nonlinear behavior contribute much to the safety of the structure as it behaves non-linearly from elastic to inelastic stage. Okay, so for the method of analysis, we have here, of course, a lot of theory. We have the elastic plate theory that can be uh, solved or it can be demonstrated in terms of a closed form solution. But since complexity will not allow you to do a very analytical, highly mathematical solution, then we go to finite element analysis, which can be very well presented in terms of software. Okay, so all software you're choosing the finite element solution. And we have also the tabular solution, which has something to do with ACI tables. Okay, so a lot of ACI coefficients can be used for such. So we go back to the differential equation for bending of elastic plates. So this is the theory regarding plates and shells that we will be discussing in case we encounter some theory on thin plates and thick shells here. Okay. Okay. For the limit analysis, which is very uh, what shall I say, classical, in the solution of those which can be solved using a finite element analysis or by ACI methodologies, standard methodologies, we can do some limit analysis. So this is now beyond the elastic range. So this limit analysis is actually an inelastic analysis or the plastic analysis in still design. Okay, so we have the two methods, the yield line theory and the strip method, which of course have other names. For yield line theory, we call this the geometric compatibility theory, and for the strip method, we have the static equilibrium theory. Okay, so this is based on the upper bound theorem, and this is based on the lower bound theorem. Okay, so for the upper and lower bound, we simply states that if this is the curve upon which the capacity, let's say this is the capacity WU versus, should I say, the load versus the deformation delta. Okay, we can just say this is PU, okay, versus delta. Okay, so we have here now the lower, okay, the lower bound and the upper bound. So the actual load will fall between these two boundaries. So if this is your actual load, in the lower bound theory, the actual load is always greater than the computed loading. Okay, based on this, lower bound is based on the strip method, and the upper bound theory is basically based on the yield line methodology. Okay, so which is safer? Of course, the yield line theory, the upper bound theory, is a little bit riskier than the lower bound theory or the strip method here, because the actual is always in between these two boundaries. Okay, for the approximate methods, which are just, of course, some are elastic and some are elastoplastic based procedures. So we have here the famous ACI method 1, 2, 3, which is the coefficient method. Okay, for the grid system, we neglect torsional effects if we consider it as a grid system. And for the more involved ACI solutions, we have the ACI direct design method and the equivalent form method. We will not discuss this because these are very old ACI methods. So, but I know we have encountered these two. So we'll start basically later on these two here. Um, Not so new but very interesting in the sense that we are able to see in a more broader context how to deal with slab analysis and design. Okay, so that's it for the introduction on two-way slab system. I'll see you on the next video to discuss uh, the ACI direct design and equivalent method. Thank you very much for listening. I'll see you on the next